So, let us continue with our discussion on heat conduction, and we are doing the final topic, and that is 1D unsteady state heat conduction in a semi infinite geometry. That is where I left you, and so the same condition continue to apply here, one dimensional unsteady state, constant property, no source, and the geometry that I have indicated is a semi infinite geometry. Last time we did an extensive analysis of one dimensional finite domain, and I have introduced that summation solution to you. And before I conclude today's lecture, I will also introduce to you the Heisler charts, which are very convenient to use in one dimensional heat conduction, because every time calculating or computing the summation, infinite summation series becomes a tedious job. So, there are charts which are available that allows us to know the temperature field, and that I am going to discuss once I finish addressing this particular topic. So, this is, let us say it is, if it is y direction, and then I am deliberately sometimes taking y along this, sometimes taking y along this, so that we understand that our choice of coordinate system, the way in which we show the direction is nothing to do with the discussion here. We should be flexible, that enhances our understanding. So, we have y tending to infinity, and that is what I said t is equal to the t infinity, or we can say t is equal to t 0, whatever you may decide. So, the problem is that and I have also introduced to you, and I said that the thickness of it may not be a physically infinite domain. Okay? The domain actually is so thick that the heat which is penetrating through this surface really does not see that there is another wall, and it takes infinitely long time, which for all practical purpose is not significant for us. So, we can treat that look, we do not have to go this far, the heat is within the time zone of interest, because it is an unsteady state heat conduction. So, therefore, the penetration of it is going to be restricted close to y is equal to 0, which is one of the boundaries. So, for all time, the temperature in this semi infinite domain is maintained at T infinity T 0, and that T greater than T, which is equal to 0 plus we noted. So, the surface temperature is raised to T 1, and that is we want to find out that how does the temperature goes. So, we can imagine that even without solving, you should have this sort of a feeling that if this represents, if this is the temperature axis, and if this represents the initial value T 0, so we can understand that look, the moment for the first 1 second or half a second, here temperature will be T 0, here temperature will be T 0. So, the graph will something look like this, the solution will come out like this. That is the solution that we expect at very short time, where we see that the heat has dropped really. So, without even solving the governing equations, we can have a feeling, and I have not drawn it in linear as a linear segment because I know the solution, but nonetheless I know that the solution is going to be, the temperature is going to be changing within this short domain, and rest of the part it is going to be remaining the initial temperature itself. So, if you look now at the governing equations, so we had this governing equation rho Cp, this is our general equation, and then we have k, which is we take as common, and then the Cartesian coordinate system, then this is our equation. I am writing this equation again and again, so that you get used to it, looking at the equation. And so, it is a one dimensional no source problem. So, as per our definition, we have set this to be equal to 0, we have set this to be equal to 0, and hence the characteristics equation is a one dimensional. Okay. This equation was the same equation that we applied to the slab geometry, which I discussed last time, but now the moment I will apply the initial and the boundary condition, these characteristics of the semi infinite geometry will come into the picture. For example, at t is equal to 0, as I have said, for all values of y varying between 0 and infinity, the temperature is going to be equal to T 0 or T infinity, and then T greater than 0, we have at y is equal to 0, T is equal to T 1, that is all on a sudden the temperature at the surface is raised, and then at y tending to infinity, T is equal to T 0. We must understand that at this particular boundary, it is also possible to apply a gradient on temperature to be equal to 0, because the temperature has become flat. So, the moment both the boundary conditions will produce the identical solution. Okay? So, that is, so the moment you see, so in earlier case what happened, we had at y is equal to 0 something, and then at y is equal to b or plus minus b, we had something with a finite domain width which was 2b. So, we could non-dimensionalize the equation, but in this case non-dimensionalizing will be difficult, or it is not much meaningful, because of the simple fact that there is no finite domain length in this particular case. So, defining a dimensionless temperature, defining a dimensionless distance will be really tricky in this particular case. So, we should continue with the dimensional form of the equation rather than the non-dimensional form which we have used in the last term. Now, subject to these initial conditions and boundary conditions, so this we can now solve this equation. The solution, of course, once again I am not going to outline in the class. So, here the solution is not by separation of variables, but one solves a plane source problem and then does superimposition and then integrates the whole thing to provide the solution of the equation. And in this particular case, what happens is, we can say that the solution will come out to be T minus T 0 by T 1 minus T 0, and that is going to be equal to in which we have introduced several things here. Two important things, I will discuss this. Alpha is the thermal diffusivity value which is known to us, which is K divided by rho Cp. Okay? So, alpha is known to us. So, the moment we can put y is equal to 0.1 centimeter, y is equal to 0.1 meter, or whatever is the value, this parameter, the argument, is known to us. What do you say? This is the complementary error function. Now, error function is like, for example, we have so many kinds of different functions you have heard. The simplest one which you have been exposed to is a logarithmic function. What does that do? The logarithmic function actually squeezes the scale. A logarithmic scale, what happens here, 100 becomes 2 if you do it with respect to base 10. So, similarly, we have various functions available to us, okay? And one such function is error function. I am going to introduce the definition of it, and the complementary error function basically means is that it is 1 minus error function, okay? So, I would say complementary ERF C, any parameter Z will be 1 minus ERF Z. That is the definition. Now, what is the form of that function? That I am going to say, that if you have ERF error function Z, then it is written as error function Z is equal to 1 divided by square root of pi, or one can do it by 2 divided by square root of pi, then the limit will change 0 to plus Z, and then it is equal to, that is the definition. So, it is again in one sort of an exponential function. So, one should be able to evaluate the integral, substitute the value of Z, and Z is the argument. Okay? Do not confuse this capital Z with y here. Okay? The entire thing is the argument here which I have represented as capital Z. That must be just like you have a logarithmic table available to you, you also have an error function table available to you, and you can give a search word on error function and you can see that how does what are the values of error function. For example, error function 0 is equal to 0, error function infinity is equal to 1, and for all practical purpose, if error function the argument becomes 3 or greater than 3, we will treat it to be equal to 1. for the sake of simplicity, but to read you may not get these values, you may get the argument is equal to 0.23, 0.29, 0.28, and then how do you compute it? You do not do the integration, okay? You have a chart just like the table, you refer to that table and you find out that what is the value of error function corresponding to the argument that you have chosen. Now, so if you take a semi-infinite geometry, the solution goes something like this. So, the solution goes something like this. At increasing time, and this is the initial temperature T0, this is the boundary temperature T0, and this is what I say is time, increasing time, that is what is represent, and this is the x is y. As you can see here, that the slope of the line essentially indicates and if you take the value at y is equal to 0, that represents the flux at the surface. Because I have increased the temperature to T1 from T0, as a result of which heat has started to go inside, and as a result of which there is a finite heat flux. And if you look at the nature of the graphs that I have drawn, the flux is changing as a function of time. The slope at y is equal to 0 is not constant, it is very steep here, it is less steeper here, and as time is going to go on and on, you will find that the slope will become lesser and lesser steeper, because the temperature differential is decreasing as a function of time. So, therefore, this we expect that the flux here is going to be a function of time. Now, in order to find this out from here, for example, we can see that we can write down, for example, we need to T is equal to, therefore, from here if you look at this expression, okay, you can find out T is equal to T0 then plus T1 minus T0 into complementary error function. Do not read it like ERFC, read it fully, complementary error function y divided by 2 into alpha t. So, therefore, I need to differentiate this term in order to get that expression on the right hand side. So, I am now looking for minus k dt over dy evaluated at y is equal to 0. So, therefore, that will give me the moment I differentiate it, okay, T1 minus T0, and then if I write 1 minus complementary error function as 1 minus this, then I can get that this has to be evaluated, okay, minus error function y divided by 2 alpha t. And this, what we are going to do? We are going to say differentiate it and then substitute in the resultant expression y is equal to 0, and that is what we are going to get. So, you can take an approximate expression of error function and define, okay, and do the integration yourself. So, or you can do a method of substitution and do the integration yourself. You can write down the expression what I have written earlier, which I have just now erased, okay. And actually one can also write error function, an approximate expression of error function as 1 divided by square root of pi e to the power z square divided by z. This is not very rigorous, but this is an approximate expression. So, you can take this expression, substitute it here, and then do the differentiation and then find out. And I will give you the final result here, which essentially is T1 minus T0, and it comes out to be so, as you see that the flux, so it is here you can find out that alpha we have a unit of meter square per second, and this is second. So, it comes out to be meter per second here, okay, and we will have the flux Okay. Let me just look at my notes for a minute, and then I will give you the flux expression in one go. Yes, it is alpha divided by q at pi by T. Okay. So, this I think there is some sort of an error here. Okay. I will correct it later on. It is not dimensionally matching here at this particular stage, if you can see. So, I was just trying to do it. Okay. So, I think there is going to be something like this is temperature, and this is centimeter per second square, and then this is alpha by T. Okay. Let me just let me not get bogged down with this. So you can actually, I do not have that expression here. So, you can do the differentiation and substitute the value here itself. Okay. So, the results of this will come here, and then you get the final expression that I will note down from somewhere, because I do not have the result, and if I do the differentiation I will take time. So, I will give you the final result later on. But what it shows here, that this is going to be only a function of t. The y dependence will go, because we will substitute y is equal to 0. So, as a result of which, what you are going to get? You are going to get the flux, which is a time dependent flux. So, now what you require is also a q average, and this averaging is nothing but the time averaging. So, therefore, if you say that you want to average it between the time span of 0 to t, then I would say that this will become equal to whatever q or minus k dt dx dy at y is equal to 0, that you have found out in the previous expression. If you differentiate it, okay. So, if you this is, and then integrate it, because this I have shown it that this is a function of t. So, therefore, this expression will be a function of t. So, you can integrate it very well with respect to time, and as a result of which what happens, you can get this, and this can one can show that this is actually is equal to 2 times the time where this is equal to the time dependent heat flux at y is equal to 0. So, this is the average heat flux is y is equal to 0. So, this I can erase it, so that there is no confusion here. So, the average heat flux is actually 2 times the instantaneous heat flux. That is what it implies. So, we can for any semi-infinite geometry, we should be able to find out that what is the temperature, and as the way I have written here, if you remember, I have written here as T minus T0 by T1 minus T0, and that is equal to complementary error function of I have written it like y divided by 2 into alpha into t. And this basically we can say that this is although we have not non-dimensionalized the equation, we can say that this is a non-dimensional temperature, in which the non-dimensional temperature is defined like this. And whatever solution, I would say that whenever you write a solution, you must make sure that if you substitute the value of boundary conditions, for example, the resultant expression must give you the correct answer. For example, if I write down that y is equal to infinity, y tends to infinity, I should get that my temperature is equal to T0. So, if I put y is equal to infinity, we know that error function of infinity is equal to 1. So, 1 minus 1 is going to be equal to 0, that means this term is going to be 0. So, therefore, t is equal to T0. So, my initial condition or the boundary condition, far-field boundary condition is exactly satisfied. So, I can know that whatever expression I have given to you is actually correct. So, we have seen that if you have a finite geometry, one dimensional slab geometry for example, we have a in Cartesian coordinate system, we have the infinite summation series, okay, and that summation series needs to be calculated. If you want to solve the transient temperature again in a semi-infinite geometry, then we have error function solution for which we have the error function table. Now, so we can take recourse of the error function table and do the calculation very easily. Only thing we have to calculate is, because what is going to be asked is we want to calculate the temperature at a certain point and certain time. So, that is what is needed. So, I can give you semi-infinite geometry, find out at y is equal to 0.5 meter at a time of 20 seconds what is the temperature subject to this boundary condition. So, you require to calculate only the arguments of the error function where you are going to put the distance of y, and then in alpha t term you will put the t, then you get the argument and then you refer to the table and immediately the answer is known to you. So, it is very convenient once you have that error function table available to you. So, similarly, as I have indicated and as I have shown that we have the infinite series solutions, and I said, or I have been saying repeatedly that computing the infinite series is going to be very, very difficult. So, in the context of slab geometry, and not only just slab geometry, in the context of an infinitely long cylinder as well as a sphere which exhibits 1D heat conduction for example, because of its theta and phi symmetry. So, what happens is we can, we did not have to do every time a summation solution. So, there are charts which are available to us. So, somebody has computed those summation series for example, or in the case of cylindrical geometry the Bessel functions, and represented the final results or the numbers in terms of charts. And the person who did it in 1947 is Heisler. I think it is S.P. Heisler or P.S. Heisler, I have forgotten the full name. So, you can find out, you see, if you just give this search word in internet, okay, what is Heisler chart, the whole plethora of graphs will come to you, and don't get scared by looking at those graphs, because those graphs are basically the representation of one-dimensional unsteady state heat conduction in different geometry in terms of lines, and that is what it basically is. So, as I have indicated that if you remember, now we are and I have shown you two different graphs, for example, two lines I have. What does this indicate? So, this is a slab geometry. I mean, I do not have to go and discuss it in great detail, because I have done it, and you should be able to see, even though I have not labeled it, you should be able to see that what I really meant by drawing this line. This essentially tells us this is a long time solution, this is a short time solution within a slab geometry, and this, how have I obtained this line? So, I have computed the infinite summation series and I have gotten this line, because this line essentially tells me, so this is at some time t, this is at another time t1, this is at another time t2, okay? t1, t2 and t3, the time is increasing in this particular way. So, as time increasing, there is a tendency for the temperature to level up, and everywhere it is trying to get to the boundary temperature, that is the steady state solution. So, this is our boundary temperature, and this is our basically the initial temperature field. So, these lines, by substituting y is equal to 0.1, y is equal to 0.2, y is equal to 0.3, y is equal to 0.4 and so on and so forth, or if you are measuring from the central line, then y is equal to 0.1, y is equal to 0.2, 0.3, 0.4 and up to 1, this is equal to plus 1, and this is equal to minus 1, and this is equal to plus 1. So, at different values of y at different times, by putting in, if you remember, there is one exponential function and another one is the cosine function. Cosine was the space function with y and the exponential function was with respect to time. So, as a result of which what happens is, by putting in the value of y and time, I should be able to find out that how does the temperature varies as a function of time, and this is the solutions that I have obtained by spending one night in the computer center, and I can generate n number of graphs. I have just shown 3. So, you can have n number of graphs, and Heisler has exactly done the same thing and done it 1947 when perhaps there was no computer. Okay? Why perhaps there was no computer at all, and this computer calculations are available. Of course, the original chart that he has proposed, those charts have undergone considerable amount of refinement and have become more accurate now with the advent of the digital computer, and as a result of which what the earlier Heisler charts, which has less number of such lines because it is tiresome. So, what we see today's Heisler charts are quite extensive. So, this solution which I have shown also in the previous lecture is for a finite geometry. So, similar solution can be obtained for a cylindrical geometry or for a spherical geometry. And the solution 1D unsteady state solution for cylindrical geometry, as I have said, is a Bessel function solution. So, one can do again as a function of the radial distance and time, because one dimensional infinitely long cylinder means it is only radial heat conduction. So, one should be able to find out that as a function of radius how is the temperature changing, okay, for different radial distances. Here different planar distances as a function of time. So, for infinitely long cylinder, what is given a different dimensionless radial distance, how does the temperature is changing? Similar kind of a graph is going to be available. For spherical geometry also similar graphs are available. So, these graphs are basically, I would say, represented in terms of non-dimensional time, temperature versus non-dimensional distance for different non-dimensional time. You should be able to see what I am trying to draw. So, this is the non-dimensional time tau is increasing. This could be, for example, in a cylindrical domain or a spherical domain, this could be the surface of the cylinder and this could be the center of the cylinder. So, what you have to basically do is you have to, if you are given a problem or if you encounter a scenario where you have a spherical geometry or cylindrical geometry or planar geometry, you have to just know that yes, it is one dimensional unsteady state heat conduction, constant property heat conduction, and the moment you understand that what is the geometry, you refer to the Heisler chart. Okay, this is planar, this is cylindrical, this is spherical, and you pick up the right one for your geometry and then you apply. So, if you will be able to calculate alpha t by r square, this dimensionless time, this is alpha t by r0 square, which is the radius of the vessel. So, you put the time is equal to 1 second, this term dimensionless time will be known. If you want to find out what is the temperature at center, then you will put r is equal to 0 and then this is going to be r by capital R is going to be 0. So, you will find that, so you are going to look at this particular line. So, you see that now my time is corresponds to this. So, this line corresponds to this particular value. So, and then you find out that it. So, this is your dimensionless temperature. Then if your dimensionless temperature is defined as T minus T0 or T1 minus T0, okay, in that case you know the boundary temperatures, and once you pinpoint the value here from Heisler chart, you should be able to find out that what is the center temperature at a time of this which corresponds to a non-dimensional time of say T1. So, it becomes a trivial exercise in that particular case. So, you are not concerned with the solution, you are not concerned with computing the Bessel functions or the summation series, okay? You are just concerned with finding out or identifying the right Heisler chart applicable to your scenario, and that will allow you to read or know what the temperature field within the system. So, I do not want to continue any further on heat conduction. So, we will like to now start discussing about the convective heat transfer process. The next 2 lectures or so we will discuss very briefly. It is an extensive subject, but nonetheless we need to understand, because convection is very important for us. So, we will talk about convective heat transfer. So, convection, as you all know, what convection essentially implies that there is a fluid and there is a flow. So, the moment we are talking about convective heat transfer, it essentially implies that we are talking of transport of heat. Now, not within a solid, but within a fluid, okay? And because of the fluid motion, heat is going to be transferred from one point to another point. So, in fluids, for example, I would say that both conduction and convection are going to be operating, and sometimes radiation too, as we will see later on, particularly in gases. Okay. So, if you want to transfer heat over a large distance, you cannot really do it very effectively through diffusion mechanism or heat conduction mechanism. Conduction is a very slow process. On the other hand, for example, I say that if I have a huge vessel containing liquid metal and I want to transfer heat into the material. So, if it is a stagnant one, and you can imagine that if heat is supplied onto the surface, it will take long time for the heat to reach in this particular or all the locations within the system itself. Okay. So, this is a heat source, it is being applied, there is no stirring present here. So, heat will take enormously long time to get distributed. So, if I want a homogeneous bath with homogeneous temperature field, then what I have to do? I have to really apply stirring into it, which will, so which creates a scenario like which we call as a thermal mixing, just like the way you mix sugar in a cup of tea, okay, is the same thing. You do stirring, and this stirring introduces convection current in the system, and this stirring therefore helps heat to be transferred from one point to another point. As such, in the absence of stirring, heat from here to here is going to be transferred at a very long time. It will take enormously long time, and which is not feasible. On the other hand, if you have convection, the convection will be very easily taking heat from one point to another point. If one can find out, if you give, so this is a length scale. If you consider this distance, then this length scale can also be, you can find out the diffusion velocity, and then you can find out that we will discuss this as we discuss the convection convective heat transfer in greater detail. So, this will allow you that how much time diffusion alone will take from heat to travel from here to here, that will depend on the thermal diffusivity value, and so that can be calculated, and I will show you in a minute. But the point I wanted to make here is that from the surface, heat will take enormously long time to get distributed over the entire system in order to expedite the flow transport of heat, or in order to get a homogeneous liquid metal containing a uniform temperature. What is needed is stirring in the system. The stirring will expedite the flow of heat. So, if you want to transfer heat from over a large distance, you have to resort to convection. There is no other shortcut to it. Now, we have seen that this is our diffusion, this was our diffusion flux, and we will say that this represents our convection flux. Diffusion or heat conduction, that is the same thing, characteristics by gradient. So, the net flux of Q in the x direction or in the y direction is going to be equal to the conduction flux So, if you say at any point, say y is equal to y1, then it is understood that if y is equal to y1, I should be able to know the y component of the velocity. I will also be able to know the temperature of the fluid here. Okay? The temperature anyway is to be known here also. So, the gradient is to be evaluated at y is equal to y1. What important thing I see, that the estimation of the total heat flux, this is a total heat flux having a component conduction and convection. The total heat flux necessitates the velocity, because I have only one, I will get an energy balance equation which will have one unknown, which is the temperature in the flow domain. Okay? So, in this particular k is constant, rho is constant, Cp is constant, and you see that T is the dependent variable, and here is an unknown which appears here, which is the velocity. So, that means unless and until the velocity is given to us, the convective flux cannot be calculated. So, all convective heat transfer problems will necessitate simultaneous knowledge of fluid flow which is prevalent in the system. If the flow is not given to you, you cannot perform any calculation. You can of course calculate simultaneously along, just like the way we have governing equations. So, we can have a governing equation of heat transfer where both convection and diffusion conduction are taken into account, and to know this we already have discussed fluid dynamics. Okay? So, a prescription for Uy is possible provided we solve the Navier-Stokes equation. Okay? This I have already discussed, and that is why our discussion always starts, we discuss first fluid flow and then we talk about heat transfer as well as mass transfer, because calculation of convective heat and mass transfer will require fluid flow, and unless we know how this can be calculated. So, it is at this stage we assume that the distribution of the flow in the domain of interest is known to us. It is either known from the somebody has solved, or I have already solved the Navier-Stokes equation, okay, and I got it, or somebody may be having just supplied it to me. It could be an experimental value which is given to us, but the knowledge of flow is already existing. So, it is not a question how do we get this velocity field, is not a question that we are asked. We are simply assuming that we know the flow field, and now the task is to calculate the convective heat transfer. That is the problem in this particular case. So, just like the way I have written the y direction total flux, okay, I could write a x direction total flux and z direction total flux. Just like the way I have taken a control volume and I have done thermal energy balance, heat energy coming into the control volume and going out in all three directions, and I have shown you this equation already. And this, if you remember exactly whatever I have said just now, that I have taken a control volume, into the control volume I have taken only conductive heat flux, and I have substituted here the Fourier's law. This term, embedded in this term are the Fourier's law, which is the constitutive relationship, or which is the flux temperature relationship. But the flux temperature relationship here is this. So, the total flux, when I say flux entering in x direction and flux going out in x direction, okay, I have to consider the two expressions together. Now, logic will tell you that if I have a three different terms, three different second order terms, okay, with regard to the divergent term here. So, this is I have an x direction derivative, y direction derivative and z direction derivative. If I substitute the total expression, not just this, I will have three additional terms, one along x, other along y, other along z, and those three terms will be reflecting this. So, one can, I am not going to derive this again. So, by performing an energy balance, one can show that the equation in the presence of convection can be written in terms of So, this is my vector now. Okay. So, I can have or I can say that if rho and Cp are constant, so I can take it out and I can represent it like this. And now I say that this is my, because this is no more the same quantity, because I have divided by rho Cp term everywhere. So, the k has become alpha and this is going to be similarly this divided by rho Cp term. Or if I write it, then I will write it like this, and then I will write it like this, and then this is also right. So, this term has appeared because I have treated that in the x direction. So, if I can expand it. So, this term, one of this term will look like this ux, and one of this term I can say the corresponding term will look like that is what is there. So, I can write down second term, third term, I can write down second term, third term. And as you can see here, the same condition applies, that the source term is known to us, thermophysical properties are given to us. So, if we apply the velocity, if we know the velocity, in that case it becomes one equation and one unknown. So, therefore, it can be solved. But as I said, that the solution necessitates that I have to do, I have to obtain the velocity distribution or knowledge of the velocity field is a must. So, therefore, the task is not just one equation, there could be several equations. That means, this will necessitate that maybe from a theoretical standpoint, I will have to solve the Navier-Stokes equation, get the flow field, substitute the flow field into this equation, and to render it one equation or one unknown, and then I can be able to solve this equation, provided I know the boundary conditions are still same. So, I have a three-dimensional domain, either the temperature will be given or the flux is going to be given, and we must understand that the flux can also be given in terms of either a specified flux as well as the flux given in terms of a heat transfer coefficient and an ambient temperature. So, the task becomes fairly complicated, okay, as far as solving the classroom problems are concerned. Now, you can imagine that there is a group of problems. So, therefore, there is no shortcut to it. Suppose if I have a vessel containing a liquid metal and I want to find out that, look, I have kept the material, okay, within the vessel, this is liquid metal, and if there are, because it is in a finite vessel, if there are heat losses from all the sides, obviously the temperature is going to be decreasing as a function of time. So, therefore, I can say that this temperature is going to be x, y, z and t. So, at any point the temperature here is going to be, as a function of time, is going to be higher than the temperature here, because this is closer to the wall through which the heat is being extracted, but nonetheless there is going to be a temperature distribution in the system because of the heat loss. This temperature distribution in the system, I want to introduce one term before I proceed further, will itself cause, even though there is no external stirrer here, it looks like a stagnant bath, but the moment I have a differential temperature between the locations, there is going to be a convection current, which we call as a natural convection current set up in the system, thermal buoyancy. Because what happens is, the density of the metal is a function of, is a state property, okay, and it is a function of temperature. So, therefore, if the temperatures are different, the densities are also going to be, local densities are going to be different, and as a result of which, what happens, where the temperature is higher, the metal will be lighter, where the temperature is lower, the metal will be small, heavier. So, the lighter metal will go up, the heavier metal will settle down, and as a result of which a convection current is going to be generated in the system, and that system we call it as a free convection current. This is a thermal free convection current. We will see when we discuss the mass transfer, we will also study what is known as a solutal free convection, and then we will see when you study combined heat and mass transfer, then we will see thermo-solutal free convection, where flow in the system is taking place because of concentration differential as well as temperature differential. So, this causes a fluid motion in the system, free convection current. So, that convection current is to be known in order to solve this particular equation. So, I wanted to find out, look, how much the temperature is changing as a function of time, or what is the extent of maximum difference in temperature between different locations. And now I am posed with a problem that I have to consider a free convection phenomena, I have to find out the velocity field, I have to solve this equation, and it becomes a very tedious task. But the boundaries here are going to be the same, we have a heat flux here, for example. I have to have either if the temperature is remaining constant at the surface, I can apply a constant surface temperature here, but it is not so straightforward a problem, because this becomes, we get to complexities, because there is a solid here. So, this is a conjugate domain actually, we have solid here and then bulk is liquid. So, it is a sandwich domain, it is a conjugate problem, and at the surface here. So, convection diffusion is present here, but only conduction is, or diffusion is only present within the solid. But nonetheless, if you want to treat this as an entire domain, in that case you will require a boundary temperature here or boundary heat flux here. So, the same kind of boundary conditions will be applicable here, what I have discussed in the context of convection. So, it is not going to be different. Now, in this particular problem, say, now what I do is I suppose put a cylinder, and I am interested to study that what time the cylinder is going to be completely melting in the system. Okay. This could be a liquid steel, which is 1600 degrees centigrade. The cylinder could be an aluminum cylinder, okay, melting point 700 degrees centigrade or 770 degrees centigrade. So, this will melt, and I am interested to find out that what should be the time taken for the melting to take place. Okay. And in certain cases, what happens is, as you can understand, that because there is a differential in temperature, the melting temperature here is 760 or 770 and the temperature here is 1600 degrees centigrade. So, there is a net flow of heat from the liquid to the solid surface. So, there is a many class of problem, even though there may be free convection, okay, current in the system, there is or there may be some forced convection also, as opposed to free if you have some stirring. What I am trying to say, that when our objective is basically to find out the rate of heat transfer from the liquid to the solid, because that eventually determines how much of what at what rate it is going to melt, because I can find out that what is the total melting heat. The total melting heat, by doing a simple exercise, should be the heat required to take this solid to its melting temperature and then supply the latent heat component. That is the total heat requirement. And if I find out that what is the rate at which heat is flowing between the two, then I should be able to find out very easily that what should be the time taken, assuming a rough or an approximate initial surface area. Okay. So, net Q, as I said, will be able to two different components, sensible heat part from its original temperature to the melting temperature. So, Q1 plus the latent heat, that is the total heat requirement. And if you are supplying heat at a rate of so many watt, okay, in that case what happens, this comes out to be the total heat requirement. And if you can find out that what is the heat which is being supplied, and that could be the heat transfer coefficient into delta T into an area. The area may be changing as a function of time, but if you take that area to be equal to the initial area for a rough calculation sake, then this gives you something in watt, and if you divide this joule by watt, you get it, and you can find out that what is the melting temperature. So, there is a problem here for this class of problem, okay, heat exchange between solid and liquid. We may not have to find out, because if you want to do it exactly, then what is going to happen? I will solve this equation, find out the temperature at the solid, and once I find out the temperature at the solid surface, what I have to do? I have to find out that what is the slope of the line. That slope of the line will give me only the heat flux, and that heat flux is this parameter H times delta T. This is the heat flux that we are talking about. So, knowledge of the heat flux at the surface will necessitate that I will solve this entire equation, establish the temperature profile and take the gradient of the temperature profile at the surface, and then only I can find out the phi. And we must note that the gradient may not be identical at all the locations, gradient can be very, very different. So, it poses a very complex kind of a scenario. So, what people have done is there is a simple way, particularly when we want to calculate the heat exchange between objects. We say that look, if you can somehow give us the heat transfer coefficient, then the flux will be known to us. So, the problem is without solving this set of equations, it is brought down to a simple case that we can say that the heat transfer coefficient is to be given to us, and then once the heat transfer coefficient is given to us, we should be able to find out for example, in this particular case the complete melting time and so on and so forth. So, let us take a simple scenario. Let us take a flat plate geometry. It is a hot flat plate maintained at a temperature of T0, and there is a flow which is taking over the flat plate. So, it is extracting heat, and as a result of which I can expect that there is a temperature difference. Let us say it is a steady state phenomena. Heat is being supplied at a constant rate, because this is the cold air which is coming at a temperature of T0, and what is happening now is as a result of this hot plate is heating up the fluid, and as a result of which the temperature of the fluid is increasing, and as we go up and up, what happens is far away from this the temperature is going to be is equal to again T0. So, higher temperature of the fluid. So, we are interested in the fluid phase, the solid wall is maintained, flat plate is maintained at. If I want to find out the point that I have raised, that I have to solve the convection diffusion equation, then find out that what is the graph, and then once the graph is known, then only I will be able to find out that what is the flux at this particular point. This gradient, the slope of the line will tell me the flux, and this flux, an average over the plate will tell me that what rate the energy is really going to the phase, or to maintain it at a constant temperature of T1, at what rate I have to supply thermal energy to this particular plate itself. Okay? So, therefore, the gradient is different, and as I have said last time in the context I introduced for the spherical geometry, that minus k dt dx at the surface is given in terms of a heat transfer coefficient times delta t for a one dimensional problem, if you remember, and in that context for a sphere I have written this to be is equal to r is equal to rs, that is what I have written. The surface where h represents the surface heat transfer coefficient. So, this I have, the slope is given in terms of the heat transfer coefficient, that I have talked when I discussed in the class that what is Nusselt's number. This expression, if you remember, I derived in the class, and in that context I have defined that the gradient or the conduction heat flux or the flux at the surface is given in terms of. So, when you have this line, this term, the total flux, okay, the total flux will reflect both the effect of convection as well as diffusion, because the slope of the curve dt over dr is going to be a function of the intensity of the flow. You can imagine that if the flow is very strong, okay, over the flat plate, in that case what is going to happen, this graph slope is going to be extremely large. On the other hand, if the flow is going to be slow over the flat plate, the temperature versus time, temperature versus distance graph is going to be not that steep. So, therefore, the slope, in the slope itself the information of fluid flow is hidden. We will continue with this.